Good morning, everyone. I see that the room is still full, so I guess yesterday I didn't scare you away, or not too much. And I thought about starting with this sort of controversial quote, and to stimulate discussion either later today or tomorrow about mathematical beauty and about what some experimental data means, whether it means some random, some picked, some because some experimentalist just took some data, or if it was all here, it would have made a difference to the sentence, or the sentence would not have existed. Okay, so let's start part 2, Beyond Precision Cosmology. This is the outlook, the outline. So we started yesterday from up there, and everything, it's in agreement, consensus, concordance, and then we started going down here, and today we're going to explore a little bit more what's skeletons in the closet. So yesterday we concluded by saying that cosmology over the past 25 years had made the transition to precision cosmology, and we saw that yesterday, and has moved from a data-starved science to a data-driven science, and this point has been hammered again by Professor Schlegel lectures. Cosmology has the standard model now, which only needs a few parameters to describe origin, composition, evolution of the universe, and different sort of observations. The parameter value are measured to % precision, but there is a big difference between modeling and understanding, which implies some challenges and some opportunities, and this is what we're going to explore a little bit more today. So let's keep this in the back of our mind. The standard model of cosmology builds on 20th century physics, standard model of particle physics, general relativity, quantum origin of perturbations, etc., etc. But if we step back, we realize that the strongest evidence for dark matter, non-baryonic dark matter, comes actually from looking up at the sky, and comes from cosmology, the combination of cosmic microwave background, the larger scale structure. You could not have that agreement unless you assume that most of the matter in the universe is called non-baryonic dark matter, which implies beyond the standard model physics. But also the universe has an accelerated expansion, and we associate that to the vacuum energy, but physicists that study the vacuum tell us that what we see out there is far too small compared to what is expected to be the energy of the vacuum. So this is also an open puzzle. Yet there has been for more than 2 decades wonderful agreement of all this new data, this avalanche of data, with the L-CDM model, with a little asterisk, because every so often you find 2 sigma tension, 2.5 sigma tension, 3 sigma tension, and then go away. This is normal because of the nature of the error bars in this field. Well, nature of any error bar, but in particular in this field, because you have a large random component, you are studying randomness directly. So let's recap a little bit where the cosmological information is coming from, both from the cosmic microwave background and the larger scale structure. So in the cosmic microwave background, we've seen on larger scale, the perturbations are basically unaltered, and so these are an image of the primordial perturbation put there by inflation. And then at smaller scales, we saw the sound waves and the generation of the acoustic peaks, and the detailed properties of those peaks told us a lot about the composition and the evolution of the universe. On the large scale structure side, we concentrated on the baryon acoustic oscillation signal, and we understood why it's such a much smaller effect than the order of unity perturbation that we see in the photons. On small scales, we've seen yesterday non-linearities comes in and erase a little bit the initial information about the initial condition. There may be other information here, but it's much harder to access. This gray area are the scales that are accessible to larger scale structure surveys. And there are a couple of other boxes here, because although a lot of the action is in here, there's still some information from out there, and I'm trying to give you an intuitive feelings of what type of information is in there without going into the actual equation and into the details. So as you change the cosmological parameters, and the change here are exaggerated so you can actually see what it happens, this shape changes, the amplitude of this wiggle also changes. So to understand that, we need to introduce a concept, which is the collapse scale. So if the dynamic, you can ask when the dynamical time, it's equal to the time for pressure support, and that defines a scale, which is called the Jeans length. Over dense region, larger than the Jeans length can collapse, and smaller than that are like sound waves. And I like to make this example. I gave a lecture here today, and you could hear me because I generated sound waves. Yet no tornado happened in this room. So those perturbations did not collapse under gravity. And why is that? Well, because it turns out that if you compute the Jeans length for air, it's 10 to the 5 kilometers. And so those sound waves are stable, no tornado in this room. So if we now scale this up to the entire universe, you can do that the same. The key issue is the sound speed of the medium that you have. And if the universe is radiation dominated, the sound speed is basically the sound speed of, it's close to the speed of light. When the universe is matter dominated, then the sound speed drops drastically. But there is another component there, that you are doing that in an expanding background. And the rate of the expansion also depends on the stuff that dominates the universe. And I don't want to go into the equation, so I'm just going to show you a movie. So the perturbation tries to collapse, the expansion is running away, and things like this can happen. So you have to take that into account, and you can see a sort of range of things can happen. And so this is what explains this turnaround here, and you can imagine the exquisite amount of information you can get from there if you can know the position and the shape of this turnaround. Now you can realize this is just at the limit of the scales the current survey can cover, but there's information there. And so again, about challenges and opportunity, the cosmic McCoy background was simple, well understood physics. Galaxies in the late-time universe are not simple nor well understood. We're entering the big data regime. The Planck satellite was 510 to the 7 pixel, DAISY 510 to the 7 spectra. Each spectra is thousands of points. DES is 3 times to the 8 galaxies to measure shape of them. So there's astrophysics, there's nonlinearity, there are deviations from Gaussianity. These are complicates the interpretation. And the name of the game starts being also precision versus accuracy. So systematic errors will be and are already the limiting factor. Analysis technique must evolve and adapt, but we do know very well how to deal with systematic error, with statistical error. We are not as good to deal with systematic error. Actually, we are not good at all to deal with systematic error. So accuracy.
What's the time scale associated with the lifetime of these sound waves?
It depends on the
Wavelength?
On the wavelength, on the sound speed, on the medium. So,
but what's the order of magnitude? Is it drastically changes with wavelength?
It depends on the medium you're in, right? So, are we talking about air? Are we talking about the universe?
We're talking about universe, right? Universe.
About the universe.
Yes.
So, well, on large scales. As we've seen yesterday, so on larger scales, then just the perturbation just stay there, and nothing happened to them, and then they oscillate when you start, when you have this within the sound horizon.
There is no dissipation.
Well, there is dissipation, but there is dissipation at smaller scales. Actually, in the hour spectrum, you see it after the first few peaks. You see dissipation, and you see that suppression. Yes.
So there must be a finite lifetime then, samples.
Which depends on the scales. Yeah. Yeah. And that will tell you about the composition, of course. Yes. And actually, we may come back to that later, because the composition will tell you the background, will tell you how this oscillation work, but it also tell you how that diffusion. And if you believe you know the composition of the universe, all these three things should give you the same cosmological parameters. And if they don't, then you start scratching your head. Yes. All right. So accuracy is the new precision. So what are the limitations of precision cosmology? We've celebrated precision cosmology and learned all the good things about it. What are its limitations? Well, we do parameter fitting in a L-CDM model or in parametric deviations from it. This does not really ensure that the model is correct. So what you can say, let me do some redundancy, let me look at reproducibility, let me look at different probes, because each probe rely on different physical processes. This is related to actually your questions. But precision without accuracy is meaningless, if not dangerous. And so maybe we should try to test the model at some point, since we now have all this precision. And we don't have a recipe on how to do that, but definitely there's something in there that will be useful. So we saw the maximally boring universe. The standard cosmological model survived this most stringent test. Deviation from it are even more constrained. Neutrino mass is within the reach of the next generation of experiment, larger scale structure. We saw that at the end of yesterday. We know that eventually something will have to give because the model is incomplete. The point is how much smaller would the observational error bar have to be before we actually realize of that. And also we saw that the module become very rigid because you only have a few parameters, and now you have many observations to constrain those parameters from different approaches. And we make the parallelism with threading the eye of the needle, and the eye of the needle getting smaller and smaller. So for 2 decades, the smaller and smaller eyes of the needle were threaded successfully. And I want to go back a moment to the Friedman equation. This is what the GR says when you apply to the entire universe. And these are the cosmological parameters: density of lambda, density of component of curvature, matter, and radiation. And what's there is the Hubble constant and the Hubble parameter. So the cosmological parameters have appeared, and H is everywhere. So what are these equations telling us? I always tell my students that each equation tells you a story, and you have to interpret the story that the equation is telling you. And in the world of Wheeler, what this is telling you is that matter times space, times space how to curve, and space tell matter how to move. So this is why you have the cosmological parameter about the composition of the universe and something that is about this function, history of the universe.
And this is in the regime, this is valid in the regime.
It is the background.
Well after the inflationary.
Yes. Well, no. In the inflation, you basically forget about all this and keep that.
But possibly a different that.
But possibly a different that. Yeah. But something like that. Yeah. Well, it has to be different than that because otherwise inflation doesn't end. Right. But, yeah. So H naught, or H, is everywhere and is very special. We mostly measure redshift and angle, and then we think in terms of distances, and that's where H come in, everywhere. We even invented units of H. Well, it's 100 little h kilometer per second per megaparsec, and then run with it. And it's also a key cosmological parameters. So you can see we have two cosmic speedometer. One speedometer is the cosmic distance ladder, and here I'm introducing tonight and tomorrow speakers, where you do what it says in the can, distance versus recession velocity. And then you have another speedometer, which is a global cosmological parameters of the model. These are two different beasts. But if we understand what's going on and we have the right model of the universe, they should be the same. And so if they are the same, the adopted cosmological model survive yet another stringent test. What if they are not the same? Then you scratch your head and you say, maybe I have a problem with the data, maybe I have a problem with the error analysis, or maybe I have a problem with the model, and I have to figure out which is which. So as precision increases, if the model is an effective model, at some point some cracks may show, but then you have to be sure that you're seeing crack in the model, not crack in your data or in your analysis. So spoiler alert. Everything you wanted to know about the Hubble tension but never dared to ask, it's summarized in this review paper, and I'm not going to say anything more about that, and I just let you listen to the 3 lecture by Professor Rees. So remember this, that we discussed the curse of cosmology, that we only have one observable universe. And because of this, we end up fitting numerical value of parameter to the observation, and therefore almost any statement is model dependent. And this makes me think of this quote by Daniel Kahneman about theories. We can't live in a state of perpetual doubt. So we make up the best stories possible, and we live as if the story were true. And cosmology has got of story in there. It's got the GR, it's got the Big Bang, it's got the choice of metric, it's got nucleosynthesis, it's got a hell of a lot of stories in there. And cosmology tends to rely heavily on models, which is what I call stories, both for the signal and for the noise. And we all know that essentially your models are wrong, but some are useful. So this is in the back of my mind, although I don't have an answer to this question. How do you test the model? And can you even do without the model? I don't think you can do without the model, but you can probably do without aspects of the model. But this is something for discussion. So now, after this introduction, let's fast forward to 2024, 2025. Starting about 2015 is what I call the golden era of galaxy redshift surveys. And this is an anticipation of this afternoon lectures, and I'm going to steal a slide from the next lecturer. And this is a log-log plot of log number of galaxies and the time. And the redshift survey have been increasing by a factor of 10 every 10 years. Of course, in a log-log plot, and if everything looks linear. But this looks linear too. And what I like of this is that, although DESI says 40 million, it's going to go for 50 million actually. I did my PhD on this data here. It took 5 years to get all the data. It was slow going, but it was wonderful, and it was the state of the art. And now 3 nights of this is the entire of this. So that tells you how that has evolved. So now I want to move on and discuss about the DESI result and cosmological interpretation of the results. And if I don't get to the end, I want to put the thanks before the beginning. Thanks to the sponsor and to the participating institution. This is a collaboration of almost 800 people. And so I cannot take credit. I'm just the messenger here. So the data release 2 is the data release that came out now in March this year, and is the largest 3-dimensional map of galaxies. And just to give you a sense, this was the footprint and in the first data release about a year, almost exactly a year ago. This is the footprint of what part of the sky has been analyzed in the DR2 papers. And you will make the connection of this circle here with what you will show about today, right? So you will make the connection, keep in mind those circles. And that's the status 2 months ago. So previously, over the past year, more than 26 papers have appeared in a special issue in JCAP of the results. And I'm going to try to give you a taste of this. And then this March, another four paper made a splash on the archive. And I'm going to mention only something about the first two. The second one, I'm going to just touch upon it, and I'm trying to summarize the first one. So we need to take a step back and try to imagine how would we describe growth of perturbations. So you have a gravity and you have an expanding universe. If you have a typical region of the universe, this typical region will expand with the expansion of the universe. So you can imagine this bubble that will expand exactly the same the rest of the universe does. However, if you have an overdense region, what will happen to this overdense region? It will start expanding a little bit. At some point, gravity may take over and will actually collapse. Of course, in an underdense region, it will expand faster than the background expansion. But remember, we don't observe distances. We observe recession velocity and redshift. And therefore, when the redshift of an object is never at exact distance, it's disturbed by what are called the peculiar velocity, the deviation from the Hubble flow. And you can imagine what the deviation from the Hubble flow is going to look like. So let me see if I can visualize it a little bit better. But what you know is that this deviation, what may seem, one man's trash is another man's treasure. What may seem a distortion of the signal, may seem noise, may seem trash, is actually not. Because these deviations are sourced by the underlying perturbations. And the underlying perturbations carry a lot of information. Their amplitude, how they grow as a function of redshift, carry a lot of information about the composition and the cosmological parameters of the universe.
Sorry for my ignorance on this, but since you mentioned this more local fluctuations from this global Hubble expansion, what are you doing with black holes?
Well, black holes are those, you want to say how they form, or if they are there, what happened to them?
I mean, how do you include them in this expansion? I mean, you can argue about this, Hubble as well.
So what this assumes is that you can average, and on large enough scales, you can describe things in linear theory, which means that if you have a small perturbation that even goes so non-linear that you actually even create black holes, if you zoom out and you look at it on average, at some point you will be able to describe it in a linear way. Whether you can do that 100%, it hasn't been necessarily proven analytically. There are people that say you can't do that. You can have this back reaction effect of nonlinear structure on the background. We are ignoring that at the moment. We are taking this assumption, which is what 90-something% of the people that work in the field do. But it's a good question to ask. So black holes are points. Once you are very far away from the horizon, they just act like points. They could be bricks, they could be black holes, you don't care. So if we could measure distances, galaxy survey will look something like this. This is a slice and then squashed, but otherwise you would actually see like a cone in the sky. But we don't. This is a simulated survey, but we don't. We use redshift, and if we interpret the redshift as distance using an Hubble law, you see that some structures are elongated along the line of sight, and some structures appear to be squished along the line of sight. And this goes back to this, if you have an overdensity, and if it expands, an underdensity expands faster, and overdensity expands slower. When you get to nonlinear structure, you start having, random velocity. And then if you use their redshift as distances, underdensity appear elongated along the line of sight, and overdensity will appear squashed along the line of sight, while a nonlinear structure will really appear elongated. So here they appear very elongated, and otherwise bigger structure will appear squashed. And so you can do that in the correlation function. So separation along the line of sight, the separation on the plane of the sky, and this is the famous butterfly plot that come from the 2-degree galaxy redshift. Very good. Remember when we talk about the philosophy in constraining cosmology and introducing compressed parameters? So we had the compressed position of the BAO, the two, the isotropic and the squashing, or line of sight and perpendicular to the line of sight. What do we do with this redshift space distortion and with the growth of structure? Well, so we compress something, number of galaxies times 3, to some compressed summary statistics, few tens of points, down to 2 quantities. There. Of course, this is not a lossless data compression. We've lost some information, although this is most of the constraining power in cosmology come from here. Now we need to add another parameter. And what is that parameter? Is the amount of squashing. So if statistically the universe is isotropic on large scales, this perturbation should be isotropic, but the redshift space distortion on large scale make them squashed, and on small scales make elongated along the line of sight. This is non-linear. We don't want to look at that yet, but we look at the linear and better model component. And so this is another parameter, and it's related to the matter content of the universe and the amount of perturbation that is in there. And here it is, even as a function of redshift. And the parameters end up being this combination of the linear growth rate times the amplitude of perturbations. So now you can say, excuse me, when we did the BAO, we did the line of sight, the plane of the sky. We were assumed that it was isotropic, and then we were using the observed anisotropy to figure out how far away your fiducial model is from the true underlying cosmology. But now you're saying that the map that I look at actually is distorted. So how can you separate one from the other one? Aren't they the same effect? Aren't they distorting something that you're supposed to see as isotropic? And I think you can see it here. The BAO is out here, signal, and this squashing and line of sight is on smaller scales. So everything is affected, but the localization in terms of scales is different, and therefore, although there is some covariance between these two effects, the covariance can be computed and is not huge, and so these two separate information can be extracted from the data. So that was the original one, 2001, and something like this as seen from the Boss collaboration, a much higher signal to noise and much larger scales. So that little butterfly will be included here. Okay, there's a lot more physical information from the larger scale structure. With clustering, and you can ask what are the constituents of matter, what's the physics of inflation, what's the neutrino mass, the standard ruler BIO tells you about the expansion history of the universe, the redshift space distortion tells you how structure form. On very large scale, you can ask about homogeneity, non-Gaussianity, etc., etc. So while we have seen yesterday about this Now I've introduced some information about that. How does it look? In summary statistics, one ends up decomposing the clustering as a function of the line of sight, and then recompress it in terms of monopole and quadrupole. And what this Redshift space distortion do, they grow this quadrupole signal, and you can see even visually how you separated baryon acoustic oscillation. You still have baryon acoustic oscillation here. You still have, although now it's hard to see, baryon acoustic oscillation signal here, and the Redshift space distortion is desampling. So even in Fourier space, you can see how the two signal get separated. Now, is this the whole story? No. There's more information in there. But to me, there is an information content hierarchy. So if you want to constrain cosmology, the bulk of the signal come from the BAO. The next, in terms of information content, come from the Redshift space distortion, which I couldn't even show here because this is the isotropic signal. And then I will show you the monopole and the quadrupole, which I didn't show. And then there is an extra information that comes from here. Remember when we talk about this shape on the larger scales? And then there is yet a little bit of information, but now start becoming diminishing return, which is the amplitude of this oscillation. And then there's something that is left on the nonlinear scale, but it starts binarized. Of course, if you do this Dirac effect, everything goes together, and then you get the final, the composed constraint. But if you do compressed variable, then you can disentangle each of the signals. Okay. I like this quote because it says, well, if you want to test the model, maybe are we fooling ourselves? What's going on? And one of the first things that come to mind is, well, you are doing your analysis. You are really involved with it. You're testing for systematics. You're testing for bugs in the code. When do you stop? And it's all too easy to stop when the answer you get is what you were expecting. How do you prevent that from happening? So there is some approach that allow you to sort of break this cycle, which goes under the name of blind analysis or blinding. And there is a nice article in 2015 in Nature about using blinding that was about both supernovae and the analysis in particle physics. But that this hasn't really been applied to large scale structure survey. It had been applied to weak lengthing somewhat, but not to actually galaxy Redshift survey and clustering. So when Daisy came along, then in my group we started asking, can we blind for cosmology something like this? And something like this, when you may have different tracers, you have different summary statistics. There are even Lyman alpha, which I think you mentioned yesterday, which is looking at absorption line in the spectra of quasars. Can you do all these things consistently? And the way to do it consistently is to do it at the map level. But blinding at the catalog level, there's many things that you can do, but you may also blind also the you want just to blind cosmology. You don't want to blind everything else. And you don't want to just add noise or spurious effect there. And so what we came up with in my research group is a proposal of how to blind galaxy Redshift survey at the catalog level. And this proposal came out by actually thinking at the clustering at the signal in terms of compressed variables. So there's a connection there that I hope you can get a taste of it from what I'm going to say. So our proposal is act only along the line of sight, so you don't mess up with the angular weights. It's not easy to blind accidentally, and you are not blinding yourself with the major systematics that usually come with the angular clustering. And then we're going to blind the BAO and the Redshift space distortion signal by applying and combining two types of shift along the line of sight. One geometrical that look like the Alco-Pachinski shift that we learned yesterday, and a density-dependent Redshift space distortion-like shift, because we do know how Redshift space distortion are related to overdensity or underdensity. And this was tested on both data and then adopted for DESI. And this is the picture of graduate student Samuel Bride and postdoc Hector Gilmarin and me when we went to the DESI meeting in Berkeley lab, and we tried to convince the collaboration that this could actually work. So in terms of DESI analysis being different from previous, not just the quality of the survey, not just the exquisite spectra, not just the number of objects, but also it's the first time that a category level blind analysis was done to mitigate what is called confirmation bias. And to boil that down into one line, remember that I say always the first thing you do when they give you angular redshift is to assume a fiducial cosmology, transforming distances, and then go and do your analysis. So then you introduce the blinding there. So you always need to assume a fiducial cosmology to get distances. So what this blinding does, it adds a blind cosmology which is not revealed and gives you back angle and distances, angle and redshift, and then you use your fiducial cosmology, but now your map is distorted because I didn't tell you what this was. But the moment I tell you what this is, you can convert your result automatically in what are the true underlying results. And then this has been there's a velocity contribution to blind the redshift space and further correction to blind for non-Gaussianity, but let's just leave that. So let's go back to this plot. Once you have the summary statistics, you have two choices. You can go the way of compressed variable, or you can do the way to full shape of direct fit approach. And what we call full shape, you can do either compressed variable or full modeling like you do for the CMB. And I think this is quite powerful, right? Because you can attack the problem from several different points of view, and you want to make sure that everything agrees. So, okay, ready for the results now?
Yes.
Okay, so here it is. Bright galaxies, now we go up in redshift, luminous red galaxy 1, luminous red galaxy 2, luminous red galaxy 3. There's some overlapping redshift with now different type of object, emission line galaxies, because you run out of this type of object. If you go far enough away, the universe becomes younger, and there's no time to produce these. And then combination, and then you keep going up in redshift until there are quasars and Lyman alpha. So definitely that BAO feature, it's very, very visible. And remember, that feature gives you distances, plane of the sky and along the line of sight. And now let's plot it. Remember, you can do the two decomposition, either the overall size and the Alco-Pachinski distortion, or transverse and line of sight BAO. The thick points are the DR2 data, and the thin point are the previous data release, the DR1. The black line is the ratio. Remember, we always report ratio with the best fit, and that line is the Planck, the CMB preferred model. And there are a few things to note here, is that, let me see, okay. So in the first data release, people started getting worried about this point and say, is that a fluctuation we should worry about? With more data, it's getting more in line with what one expects, so it's probably statistical. It's actually, it is statistical. And then the other thing happened also with these guys here, In the previous data release, people were worried about this point, but now with smaller error bars, it's not that discrepant. And when you put it, yeah.
Go back to that for a second. You did all this elegant blinding to
Yeah.
make sure you didn't have confirmation bias. And I wonder, what's the protocol for after you unblinded the data, looking at individual data points and worrying about this one or that one? Does it follow a particular procedure, or are you now
No,
free to?
it's so you freeze everything before blinding, and if you do something after blind, you have to declare what you
Sure.
do so people can
Right,
follow.
but I'm more concerned about the issue of, at that point,
At that point, you have to
introducing
accept it.
your human bias
Yeah,
or whatever
yeah.
it is to say, this one's further from the model
Yeah.
than the other ones I'm suspicious of.
Yeah, so you don't change anything, but you just look at it, and especially because your reader will look at it, and your reader will ask you what's going on there. And so you don't do much. You say, according to us, it's just statistical, but let's see with more data what happened, and with more data, this is what happened. But you don't change your cosmological interpretation. You just live with it.
Okay, I mean, in reality world, I see, people talking about certain data points or papers that go, well, if we remove this data point or whatever. So
Yeah.
I guess what I'm saying is, this seems like a more pernicious
Yeah.
form of confirmation
Yeah.
bias than,
Yeah.
Your pipeline. Or
Yeah. Yeah, but if you do this and then you publish your data and your interpretation and say, this is it, then a posteriori you can discuss and whatever, but at least you have this is it. So,
Actually, could I follow up on this? So I'm a quantum physicist, and I have to say that even though it's now become the fashion in this field to do blind analyses, I'm kind of ambivalent about the whole thing. And the reason so it's also partly historical, right? Most of the great advances in particle physics have been done without blinding. And so what I'm not convinced that had we done blind analyses in the discovery of the electron in the 1890s, I'm not convinced that we would be further ahead than we are today. So the case for blinding has not been made in my opinion. The second thing is that you do a blind analysis, you open the box, you get results that's quite different and suggest something spectacular has happened. There's the danger of being fooled into thinking I made a discovery because, after all, I did a blind analysis.
yeah,
But that's it's really could be really dangerous.
Yeah.
So I'm it's not that I don't want to do blind analysis necessarily.
Yeah.
But we've got to be very careful. So
Yeah.
for me, what is far more important is to make sure that young people develop a sense of scientific integrity
yes.
in the end.
Yes, yes. So blind analysis is not a panacea, and it's not a magic wand. It's one more tool on your tool belt that protects you a little bit against experimental bias, but there are many other biases out there, and it's good for parameter fitting. But if we really want to know, and that I will try to hammer this point even at the end of this lecture, parameter fitting only gets you so far. You may need to move beyond parameter fitting, and at that point, we are not completely equipped to actually do that, and that's where great physical intuition becomes crucial.
I want to follow up on this line, but because so my question is, when Desi's blind in this procedure that you do, the question I often have is your analysis, that stage of analysis, is it something that is done by pipeline and there are no choices, or is it something where you run a pipeline, you look at the results, you tweak some knobs, and you do have choices? Because if it's the former, then I feel like somebody's blinding is kind of a charade in that you go, well, I'm going to run this pipeline. Before I do it, I'll add a random number. Then I'll run my pipeline. Then I'll take out the random number. What's the point? But I know people who will extol the blinding of their work. But when I look at it, I go, oh, you just ran a standard package on the data.
No.
So what was the point? So with Desi, do you have choices in the analysis that you have to blind yourself from at the stage where you're blinded?
So the idea is to separate the cosmology from everything else. So all the choices that you may want to do, you want to make them not contingent of what the cosmology is. So that's what blinding forces you.
What are some examples of choices that you're making at the analysis step where you're blind?
For example, it could be, I don't know, at what scales do you stop your analysis? What the smoothing scale you do for the reconstruction? What kind of bias HOD do you use?
And there's no true optimal answers to those things?
There's no true optimal answer, but what you want that those choices are not driven by the cosmology. And you could do it some other way, of course, but that's the way that you can actually test it on the data rather than testing it on simulation. Also, you can blind away from Lambda-CDM, while what you are used to do if you do that in another is just, I'm doing it on simulation. Most of the simulation are in a Lambda-CDM, so I'm testing that, but still within the Lambda-CDM, while this blinds you away from Lambda, because we don't know if the universe is Lambda-CDM. But again, it's not panacea, it's not a magic wand, and it's got to be used within the limit of applicability and usefulness. Okay.
I have a very much less profound question. Is the DR1 sample included in the DR2, or are they disjoint?
Yeah.
Okay.
Yeah.
Can I ask you, so these fours are correlated, right? So you have
Yeah.
4 variables and the free ratio, so only 3 of them are independent, or?
No, so there are correlations, but they're not that big. They're very small. The only thing that is correlated is one bin of the ELG with the last bin of the LRGs, but then you can combine them and take care of that. So what is...
If I try to get the right top, I can probably take the ratio of this left forearm and right forearm.
Oh, so wait.
Yeah,
So these are not independent from this.
Okay.
Out here is the same information. It's just different packages.
Yeah.
This and this, like this and this, are a little bit correlated, and that correlation is included. And then there may be some tiny correlation between redshift bins, unless the redshift bin overlap, and then that's a count. So when you put it all together, within a Lambda-CDM model, if you don't want to say anything about what the cosmic microwave background tell you about the sound horizon or radiation drag, all you can say is this combination of H0 and the sound horizon and omega matter. As we were seeing yesterday, if you only have one redshift or a small redshift range, each sample will give you a degeneracy in this space. But as the redshift changes, the degeneracies rotate. And if your sample becomes extended in redshift, then this degeneracy starts being broken. And when you put it all together, well, you end up landing there. So far, so good. So DAISY data alone, you can constrain omega matter to 3%, and the combination of H and RD to below 1%. Now, if you want to break this degeneracy, you need to add extra information. And one that is being used is the big back nucleosynthesis prior on the baryon density. And in the next slides, I'm going to explain very briefly what this is. But this is a prior on the physical density of baryons. And you can also add the angular BAO on the cosmic microwave background. And the nice thing is that this now get down to below 1%, but now in H, not the combination of H not RD.
So, BBN, Big Bang Nucleosynthesis,
Yeah.
measures omega BH squared.
Yeah.
How did you extract H?
Oh, because this quantity depends on omega baryon H square and omega matter. So assuming standard early time physics, with the omega matter that come from here and the omega baryon H square that come from here, you separate H out.
Okay.
And for those of you who have heard about BBN, and So for those of you who haven't heard about BBN, let me just say that it's a wonderful piece of physics where a group of 2 people went and looked at the most pristine absorption region of the spectra of quasars and find out what the deuterium abundance is there. And that is related to the primordial deuterium abundance. Deuterium is only destroyed in the evolution of the universe. And that feeds into the calculation of the primordial nucleosynthesis. Remember the first 3 minutes in the evolution of the universe? And that's driven, and that's therefore give you a handle on the physical density of baryons. At this point, the observational error bars will give you an uncertainty on omega baryon h square that is that. The actual uncertainty is this. And this uncertainty is driven by the nuclear reaction rate uncertainty. Even though a few years ago, when this became obvious, even without doing a full Monte Carlo of this type of error, then this motivated the Gran Sasso-Luna collaboration to actually nail down the nuclear rate uncertainties. But even with that, with their effort that shrunk those errors, today you have an important component on the uncertainty in omega baryon h square, not just coming from the observation, but coming from the nuclear reaction rate. I find this is quite impressive. So the next question you can ask is, okay, is Planck Lambda-CDM the same as Desi's Lambda-CDM? And we discussed this plot a little bit earlier already. So in this plot, natural unit for large scale structure H naught RD times omega matter, DR1 are the dashed one, DR2 are the blue one, and Planck plus act is here. Are we happy with this, or are we not happy with this? Let's quantify that. It's 2.3 sigma discrepancy between BAO and CMB in Lambda-CDM. It becomes 2 sigma if the lensing signal from the CMB is excluded. And it was 1.9 sigma in DR1. Of course, 2 sigma does not attention makes, but it's something that is going to keep popping up again as we keep analyzing the data by relaxing the assumption on the underlying model. So when you have something like this, then you look at it a little bit closer, and you say, well, what happened with Desi plus BBN, or Desi plus just the position of the first peak, and not everything else that is going on in the acoustic peaks and the damping tail? And you end up with something like this, and like this if you add the position of the first peak. And I noticed that the CMB geometric degeneracy is a line on the omega matter h cube line. So let me just give you a reflection, which is not anything particularly quantitative. If I want to break the model, it's very easy to break the model. It would be very easy by moving this way, while the discrepancy between BAO and CMB happen along the degeneracy. Along the degeneracy, it's very easy to move this banana plot, because any little perturbation will move you along that degeneracy. And these constraints are usually much more robust in the perpendicular. But this is just sort of a generic statement, and then what we do with it, we'll see. And then you can start doing other combination. Then instead of just the position of the CMB, let me put some priors, like omega baryon or omega baryon and baryon plus cold dark matter, because this is a way to extract only the primordial information, rather than also all the secondary from the CMB. But remember, CMB doesn't do compressed variable, so we have to do it in this sort of half-house way. And so it seems to tell you that this shift here comes from the secondary rather than from the primary. That it's early time probably to do any more confirmed statement. Okay, so let me move on. Supernovae in Lambda-CDM. Shoes lands here. DESI plus BBN lands there. Now there's no CMB in here. It's 4.5 sigma tension. Here we are again. Supernovae, these were with anchors, uncalibrated supernovae, just by looking at the shape of the expansion history, constrain omega matter. And you can see that omega matter seems to be all over the place. DESI is below 0.3, CMB somewhere above 0.3, and then the supernova wants a even higher omega matter. So, yeah. Is this so big tension of not to combine the data set? Well, if it's just around 2 sigma, maybe it could still be statistical, and let's combine them. And combine them and go beyond the Lambda-CDM. And now going beyond the Lambda-CDM, I should say, are we doing parameter fitting, or are we trying to understand what's under the hood? Parameter fitting we know how to do. Understanding what's under the hood goes back to your question. And so you end up seeing table like this. And here I want to highlight, if you allow curvature, not just having a spatially flat universe, yes, it wants the universe pretty much flat. If you say, well, maybe the equation of state of dark energy is not -1 like lambda, it's still constant, but it's different from -1, then it turns out that, well, the data want something that is still consistent with -1. But is that the whole story? So say that we step back and we say we want to explain cosmic acceleration. There are 3 choices on the market. One is lambda. One is we throw away gravity as we know it and we substitute with something else. After all, we tested GR up to solar system scale. We are extrapolating to some like 13 orders of magnitude, and we assume it still works. Maybe there's something there. Or maybe say dark energy is a dynamical quantity, and therefore its density, the strength is not constant with time, but it evolves with time. And then if it evolves with time, then the theorists have a field day, but then somebody come up with some parametrization and say the equation of state, which is pressure over density, if it's -1 is the cosmological constant, or we make it at W not WA model, where as a function of the scale factor it goes like this. This is the value today, and this is the scale factor. It goes in the exponent of the redshift dependence inside the integral of distances. So it's convoluted to see what their effect on the distances is. So in interest of time, I'm showing you what the constant W was for DR1, very consistent with -1. When you allow this W not, and it's still consistent with -1 in DR2, when you start open it up and say it's this W not WA model, then you end up with something like this. So what's going on? So this is a W naught, this is a WA, Lambda-CDM lives here, the DESI constraints are here, they're still consistent with Lambda-CDM. As you move along this degeneracy, what is simply happening is that you allow dark energy to sort of change as a function of time, but you still fit those distances, and the wiggling happen where the data have little statistical power, typically a low redshift, where there's not a lot of volume, and therefore the error bar on the BAO is very large. So that's what's happening along this degeneracy. But then you add information about the cosmic microwave background, no lensing, with lensing, or just the position of the peak and the primary, and then these things start shrinking and moving away from that point. So you scratch your head and you think, what's going on? You try to quantify that, and it turns out 3.1 sigma with the full CMB. Then you add supernovae, 2.8 sigma with the Pantheon supernova, 3.8 sigma with the Union 3, 4.2 sigma with the SCR5. what's going on here? Well, remember when we discussed omega matter? The CMB wanted an omega matter a little bit higher than what DESI want, and the supernova want an omega matter that is even higher than what DESI want. Now you put everything together, but you give the model more freedom in this equation of state of the energy, and so the model bends to actually try to fit all the data, and it bends whichever way it can to compensate for this mismatch in omega matter. So this is those two sigma omega matter tension that we saw before that are re-emerging under this light. So this attracted quite a bit of attention. And when things attract attention, then you start slicing it, decomposing, interpreting, and so on and so forth. And then the ACT result come out, which is this ground-based 10-meter antenna to look at the cosmic microwave background with the polarization, and they combine with Planck, they go to much smaller scales, and this thing that before it was purple, it become green and finds better agreement. It's early time. Is it because they get a different polarization signal and therefore a different tau, different large scales? We know that internally in the CMB there's a little bit of tension between large scale and small scale, so this equilibrium can be moved. Or maybe because the lensing is different. By going to smaller scale, they get a better handling on the lensing, and maybe that's changing. So before I conclude, however, I want to ask one question. Where are we? And then I move on. Again, the ESI is along this degeneracy. All the other data are along this degeneracy. If I wanted to break Lambda-CDM, why the universe didn't break it by moving this way and this way? He decided to break it by moving along the degeneracy. Why? I don't understand. All right. Is there anything else that I should worry about?
Licia, can I just ask you, does that depend a little bit on the pivot that you use for the model, the dark energy model?
So the pivot, the data tells you what the pivot is, because the pivot, it's where the data have more statistical power.
Right, but the parameterization you're using has its own.
No, I can
Right.
I can draw it.
It has a of equals 1.
The data drives the
The
pivot.
CTL.
Yeah, but the data drives the pivot.
Okay.
So if you have W of z as a function of z, W naught just move this up and down, and WA will do something like this or something like that. But then, oh, thanks. But then when you throw this into the data, what the data does is renormalizes everything so that this may go something like this. Oops. And this will go something like that. And this becomes the pivot, which is where your data are mostly constraining. And in the case of the ESI, this pivot ends up being around Reshi 0.6, unsurprisingly, a little bit above 0.6, unsurprisingly. So a lot of the effect is hidden a low redshift, where the supernova actually get really good data.
Wait, say that again. You're saying most of the effect does come from the low redshift?
Well, in this parameterization, if I move along that degeneracy,
Yeah.
then what I see is that along that degeneracy, things align so that the data that are here, and especially here where I have most of the statistical power, are still consistent with Lambda-CDM. And it's hiding all the differences, most of the differences at low redshift. Of course, you hide the differences where you don't have data.
So pivot point is just parameterization.
Yeah.
You can choose anywhere.
The
We don't
data
use-
itself will actually tell you. So you put
Right.
that in the parameterization, but the data will readjust the things,
So
and
the
then
one
you
we
can.
use, W naught WA
Yeah.
is given by Eric cylinder, but we don't need to do yeah.
But it's still those
Still,
components.
yeah.
One component that goes like 1 minus A, and the other component that is just a constant.
Well, I know what you're getting at, and I looked into it. There's a reason they picked that particular parameterization. It makes the math simpler.
Yeah.
It really does. It comes from the conservation of energy equation. That's why you expand in terms of W naught and A. But we can talk about this later. There's a debate we've been having internally. We'll share that later.
Okay, so is there anything else we should worry about? Because otherwise we don't have much time for questions later, and there are another couple of things that I want to tell you. And remember when we talk about neutrino masses, the BAO gave you information about the background expansion, but it gives you a handle on omega matter. So that breaks the CMB degeneracy, and therefore you can't get information about the neutrino mass, and you end up having a very tight constraint on the neutrino mass from DESI plus CMB. Very, very tight. Some of you may be uncomfortable because the minimum neutrino mass limit, even in the normal hierarchy, it's 0.06, and this is the 90% limit. So we're really getting there. What's going on? Well, the priors matter, because if I now say, well, this is unphysical, I put my prior here, then of course I'm not going to get the same answer. And when your prior matter, then you should worry that the data don't overcome the prior. So what's going on? Remember the omega matter mismatch? Omega matter versus neutrino mass. The cosmic microwave background was this degeneracy. Of course, neutrino act like radiation at that time, and therefore you want to keep this combination constant. Then the large scale structure comes along and gives you a constraint on omega matter, and of course you end up cornered down here. If you want high omega matter in the early universe where some of that matter was radiation, and you want a low omega matter in the late universe when some of that radiation becomes matter, the only way you can do that is pushing down that component of matter, pushing it so much down that somebody had the brilliant idea to extend that plot to negative neutrino masses. And when you do that, surprise, surprise, the data wants a negative neutrino mass. No, I'm not saying that neutrino have a negative mass. I'm saying that the model plus the modeling is not a good fit to the data, and therefore, if you add this extra degree of freedom, it mops it up.
So, I mean, you showed the supernovae and the BAO in the low redshift universe disagree about omega matter. So in this case, you're saying, well, if I go with the BAO low omega matter, then you can push it into the neutrino sector, but you don't have supernovae in this.
Decided not to put the supernova in this. We will change the story.
So,
yes.
I mean, is it fair to say with all of this, now just taking a big step back, you have these 3 data sets. They're our best data sets that we have. They have tension with each other. Depending on which model you use, it's just going to shove the tension. It's going to look like different signals. None of them, maybe it's obvious this is the extension, but we're still left with saying these don't fit each other very well, and so we have tension.
Yeah, a 2 sigma, it's not a tension that you throw everything out of the window, but that 2 sigma, it's biting us in the back when we do things like that.
But it's more than 3 sigma.
When you start combining everything.
We have no choice. I mean, getting back to our blinding conversation, and I'm going back to our blinding conversation, right? We did all this work to be really careful about confirmation bias, and then when we start seeing tensions, we go, maybe I won't use that data set. I'll just look at DESI and this, and that's the problem to me, is where confirmation bias comes in.
Right, so as expected, if you then extend the model and you say area W naught, WA plus massive neutrinos, now the neutrinos masses becomes positive again. Duh. So what I want to show you very quickly, because it would not be, oops, what did I do? It would not make justice to the people that actually made all the effort. Why? Go.
This similar study for restricting W bigger than -1. So W less than -1 is also unphysical from
It's a parameterization, okay? So let me see if I can now do this. So back to DR1 when, what is this? No. What? I don't see that. What's going on? Let me see if I can. What? What? The universe is trying to tell me something. Why do you have a screenshot that I don't see? Okay, sorry. Let me do the following. Let's kill this. I don't know why this is. Okay. So remember the information about the redshift space distortion. So here they are as a function of redshift, going to higher and higher redshift and adding that constraint that we saw with the 2 red arrow, and one end up combining with the BAO, then one end up with that little constraint there. So what does this mean? Well, this is telling you first that the amplitude of fluctuations, that the weak lensing was finding a little bit lower than what the CMB wanted. The DESI finds in agreement with what the CMB wanted in a Lambda-CDM universe. But also that now you can say, well, I have some information about the growth of structure. I have information about the background. I know that in GR, the background tell me, at least in linear theory, how the growth of structure should go. If I have deviation from GR, then I break this correspondence. Do the data find a breaking of this correspondence or not? No, the data don't find any breaking of that correspondence, which is interesting. Now, the error bars are still large, but it's a nice game to play. So I really need to conclude. And so, in conclusion, DESI plus BBN, 0.85% constraint on H0, still in tension with shoes. DESI flavor slightly lower omega matter and higher H0 RT than the CMB, but 2 sigma does not a tension make. Tight constraint on curvature, W is still -1. When you look at the WWA parameterization, desilanol is consistent with Lambda-CDM, but when you add other data set, then you have varied degrees of evidence for dynamical dark energy. There are 2 tight limits on the sum of neutrino masses in combination with the cosmic microwave background. Do you find this puzzling, tantalizing, interesting, or exciting? The growth of structure is fully consistent with GR, and the amplitude of fluctuation is in agreement with what predicted by the cosmic microwave background in Lambda-CDM. More to come, 40 million redshift in the can. Stay tuned, and thank you. So, one question that you should have in your mind. How is that dark energy related to the distance ladder and the Hubble tension? It makes it worse. Doesn't solve it. So how do you test the model if it's really that we are doubting the model? Certainly parameter fitting is not sufficient. And I want to go back to an historical consideration. When did we accept dark energy? Flatness we knew from the 1980s. The CMB first peak was nebulous until 2001, but geometric degeneracy is affected by geometric degeneracy. Low matter density, we had a lot of evidence, but the focus was after with Kobe. Age of the universe, early to mid-90s, there were objects that were older than the universe, but a lot of it hinged on the value of H0. And Adam, you may confirm what I'm about to say. What I think that made it was this data set. So if you have this distance with respect to a model with respect to redshift. There was a deviation, but the deviation could be explained by dust. Exactly. Until you actually see something like this. And you cannot become dimmer and then brighter again. So it was a qualitative different result than parameter fitting. This is qualitative, not just quantitative. That and the 3 line that was crossing in a plane, that what made it. So I'm going to, if I leave you with more questions than answer, this was my goal. I'll leave you with 2 quotes. One by Tim Maudlin, how much we've learned in the past 20 years in the history of the visible cosmos, in the whole prior of human history. And another quote The research community has been actively looking for deviation from Lambda-CDM for 2 decades. The one we may have found make us wish we could put the genie back in the bottle. And that's from yours truly. And I'll stop here. Thank you.
So we already got a lot of questions, but we still have
Please use the microphone for the online participants.
Thank you for a really marvelous talk.
It does seem to me that one question that really needs to be answered before we can even talk about looking for deviations from the Lambda-CDM is, are these tensions being generated by the pipelines people are using, right?
By, sorry?
The pipelines which are being used and the instruments. And so I know that there are people who are developing simulation-based inference in cosmology by generating, ensembles of model universes. Now, what I don't know is whether these simulations are sufficiently detailed that, in principle, these different experiments, DAISY, etc., could use these simulations to see whether, if everyone used the same simulations, would they actually all agree? Because that would be good to know, yes or no. Okay. Because if the answer is that they all agree, then at least that might suggest that there's nothing wrong that in the pipelines and the modeling of the instruments are good enough. But that seems to me something that really needs to be done.
Okay, so there's a lot to unpack in that question. So within DESI, what's happening, although for DR2, that is so recent, this hasn't been published yet, is that the same analysis is being done in several different ways by subgroup within the collaboration. And so there is the compressed variable. Even in the compressed variable, different type of modeling are being used. There is the actual full modeling, and they all agree. And so if it was something in the pipeline, these are different pipeline effectively, different even, not even pipeline, even modeling that enters even before the pipeline. And this end up agreeing. And so it's hard to think if there's something wrong in the modeling, although, again, you can look for something that you know what you are looking for. But the unknown unknowns, these are the more difficult to actually find. So how do we find unknown unknowns? This is something that we need to discuss because we don't really have a recipe for that. But the key is, let's take different observables that rely on completely different physics, completely different telescope, completely different everything, and see whether they agree. And that was the wonderful success of precision cosmology, because for 20 years they did agree. But now, as we shrink the error bar and we make them tiny, we start seeing that something don't quite agree. And then now we are there thinking, what is going on? This full forward modeling that you are talking about, this simulation-based inference, it is very powerful if you can put into the simulation everything you know about. But you cannot put unknown unknowns in there.
It is true you can put unknown unknowns, but what you could do is, have the leaders of the collaboration dump in random bits of new physics that no one besides the leadership of the collaborations know about, and then invite people to actually
so that's what the blinding does. So the blinding does that into the data and put deviation from Lambda-CDM there that you don't know about.
So I guess what I'm saying is that this could be done on data which are simulated, because there you can actually introduce all kinds of strange distortions that people do not know about. For example, this is what we did to convince ourselves that we knew how to look for the top quark, right? Our collaboration leader dumped in random bits of new physics, including a top quark mass, and actually we failed miserably. But that would be a very important thing to try.
So simulations are expensive, and One is getting at the limit of actually what one can do with the simulations. And you need a lot of simulation also to fully understand the covariances. And so doing that with simulation, it has this limitation, which doesn't mean that it's not being tried. Working with summary statistics, with compressed variable makes it a little bit easier, because since you are extracting a feature, you can distort that feature, and then so, for example, blinding can give you difference between the growth of structure and the expansion history. It can give you a scale-dependent growth, which you don't have in GR, and so we have that for the moment to test. But yeah, there's a lot, and we can't do everything at the same time coherently. Cosmic microwave background, larger scale structure, and supernovae, and do a full simulation of it. We're not there yet.
I have the microphone. Is it on? Maybe it's on. Very nice talk, by the way. Really, really nice. So I feel like we keep trying to stay away. I keep trying to stay away from the philosophy of science because I'm an experimentalist, but I keep feeling drawn in to this, because at the end of the day, now we're looking at final results and we're going, what does this mean? Okay, so I have a slightly different question for you. Wearing this hat where we're trying to say, is Lambda-CDM all there is? Is that the model? Is it right? Or have we broken it? Does it not work? Okay, so you have the DESI CMB supernova results, and let's just say, for argument's sake, it's some evidence of some breakage, crack, or something. You have the Hubble tension, okay? Now, as you pointed out correctly, right, that one doesn't solve the other, then those would be different cracks. And so my question for you is, when they're not connecting, but you're seeing multiple cracks, does this make you think it's more likely or less likely that Lambda-CDM is broken?
So let me answer with an analogy. Do you remember that at some point I had this sort of temple where we were adding pillars and had a roof on it? I have the impression that when we do parametric deviation from Lambda-CDM and we add the W and we add this and we add that, what we are working on the roof, on the decoration of the roof. We are not looking at the columns. We are not really figuring out, do we have to move this column? Do I have a column that is cracking? Do I need to add another column there? Do I have the right column even? Do we have to take away a few and put some other ones? We're not doing that. And so we are stuck. We just say, let me throw away this data and then add this other data, and we are decorating the roof and the front of that, of that roof. We're not looking at the column. And I think because for the past 20 years, we've learned spectacularly how to do parameter fitting. We've learned spectacularly how to decorate that roof. And we keep doing that because that's all we know how to do. But maybe we should be doing something else. I'm not saying that the model is broken. I'm saying that, are we looking in the right place? But I don't know if we have the tools to do that. At least these are not the tools that we teach our students and our graduate students, right?
So I have a question about omega m. So since already you introduced like a redshift dependence for the dark energy, like, can you actually do the similar thing to omega m? Like, because it's kind of reasonable to think that maybe, let's say, dark matter is decaying really late time, and then go to the radiation, redshift quickly, and then maybe it's explained or some of the tension, or I don't know if you.
So yeah, so when you put, as long as you look at the background expansion of the universe, which is all we do when we put BAO and supernova, you can put it into an omega matter as a function of redshift, or you can put it in a W as a function of redshift. It's basically it's the same equation. The thing is, at redshift 1100, but there you also put the perturbations because you have no simple way to disentangle the two things in the CMB. You want an omega matter that is really a little bit higher than DESI. Then DESI gets a lot of statistical power in the intermediate redshift, and you want a lower omega matter. You can make it fit with the supernova because you can sort of calibrate one with the other one if you forget about H0. And then at lower redshift, you want it high again. So you want it high, low, high. You have to increase it at early time, then decrease it at DESI redshift, and then you have to increase it again for the supernovae. So, and then you need to do something for H0 because now H0 wants.
So my decaying dark matter will be dead. Then I go back. Other question?
There was another question.
Yeah, I'm debating whether or not it's worth asking now or later at lunch. Yeah.
Yeah, I'll just throw one out there. Okay, since we entered to the realm of philosophy of science, because that's what the question was about, I just wanted to emphasize there were a few key things that you said early on in your talk that we really have to pay attention to. You said that we have stories, and these models are just stories. They really are. So, all right, there's that. There's also, what is blinding doing for you? You also mentioned that when do you stop the cycle of iterating on your thing? I think that's the main thing that it does for you.
Yes.
And when it comes to other, Adam, you were questioning, well, what can you do? I mean, the whole point of the blinding is so that you don't do this stuff. The problem with all this is that in the end, what we are doing to create these stories is we're using inductive reasoning to figure out what is the theory behind all of this. That is an ultimately human and messy process that you cannot quantify. That's where the disconnect is coming from, I think, in terms of there's this blinding that is quite useful in some respect, but deep down, it's human stories. We've made a decision on what theories to write down, and we have to live with it. I don't think there is an easy way to address that fundamental problem and how we actually do science.
Well, if I could just answer just a little bit back, I feel like we're too quick often to say, okay, this data isn't fitting, so what's the new story? I want that story now, or I'll discard the data and I'll stick with the old story. And I think we have to be more comfortable with the discomfort of sitting there sometimes going, the data doesn't fit, I'm not sure what's going on, we're a little bit in purgatory. And I think we're in purgatory now, and I don't think we should be fighting so hard to either hold the model or grab onto another phenomenological model, but live with that discomfort for a while.
Yeah, and to echo that, I'm losing my train of thought. You just said something in terms of there was tensions. Basically, how do you know when you need to start excavating the foundation and start? It's the data, it's the tension that tells you that. And so, in that sense, yes, you do need to sit with it for a while to see if it's if it's because you're analyzing it incorrectly in the way that Harrison was talking about, or it truly is a theory. So yeah.
But it's if you have a house, if you own a house, you are supposed at least once a year to go down in the basement and make sure everything is okay, right? So periodically we should ask, are the pillars still okay? And what does it mean being okay or not okay? Yeah.
One more question.
When you gave us the answer, you have to learn how to parameterize beauty.
I was just going to make the comment that I see these plots with these multicolored exclusion regions or whatever. It reminds me a lot of particle physics, which is like you have these things like the CKM triangle or whatever, where this program ends up working out and you localize things exactly. But it seems like rather an odd fit, really, for observational science at the end of the day. I mean, I think there's no guarantee that this program will converge, right? There's lots of examples in the history of science where promising programs just don't converge. Like it just turns out that you have the wrong approach and that you're not going to be able to answer the questions that you have with this type of approach. In particle physics, right, you can generate new data. I mean, it's expensive, but essentially straightforward to just generate more experiments every second. And here you're in the exact opposite context where you can never do a second experiment. You have the outcome of one random throw of the dice, and maybe you just learned as much as you can from it.
Yeah, that's the nightmare scenario, I think. There's another nightmare scenario, but I think we're gonna talk about that in the round table or something. Sure. Yeah, maybe, yeah.
Quick question. So I think Lambda-CDM is in a category of beauty, but how about the W0, WA, what you call WOWA CDM? Is it in a category of beauty or it's in a category of ugly?
It's in a category of an effective parameterization that if it gives you something that is consistent with Lambda-CDM, you go fine. If it gives you something that is inconsistent with Lambda-CDM, then it's surfacing some problems, but you don't know what the problem is, and you don't even know if it's WOW or if it's negative neutrino masses, you don't know what it is, but it's surfacing something. So it's useful, but I don't think we can even discuss whether it's beautiful or not.
I'm just curious, but how do you stand on Occam's razor? How do you feel about that as like the whole Lambda-CDM stuff?
Very interesting question. So we've always been driven somewhat by Occam razor, and we always had like Occam razors in the back of our head, and we've even formalized it in terms of Bayesian evidence. When you do model comparison, and then if you add extra parameter, when you add complexity, then you have to have a certain delta log likelihood, because otherwise n integrated in the posterior, you know. If you add the complexity to a model, and you add complexity that is unphysical or doesn't have a simple physical interpretation, how do you weigh that complexity? So can we actually apply the Occam razor as it is? A typical example is negative neutrino masses. So you add an extra parameter, you find the fit improved by a certain delta likelihood, and then you say, well, the evidence wants that, because it's only one parameter and that many delta log likelihood. What does it leave you with? It's unphysical, right? So it has definitely value. In all physics, we want simple things. We believe they are closer to reality. But we need to take it with a little bit of a grain of salt, and don't just count the number of parameters, complexity, and delta log likelihood. Maybe I'm not answering your questions. I'm just putting out even more questions there.
But you don't flatly deny it.
Sorry?
You don't flatly deny it.
No. I think it's really useful. Why would you have an extremely complicated model with a lot of extra complexity if it's not needed by the data? Now, the true model may actually be much more complex than the description you end up having of the data, but model are idealization, are simplification by construction. And so there you have Occam razor built in.